Hello and welcome to another edition of Miles to Go. I'm Miles O'Brien. I'm a little under the weather, so I apologize for sounding stuffed up. On the big island of Hawaii, the Kilauea volcano is as active as it has been in many years. Here's how it began. On Monday, April 30th, the crater floor of the volcano cone called Pu'u collapsed. There were a lot of small earthquakes, and a larger eruption seemed likely. Magma started moving like killer molasses toward nearby communities. On Thursday, May 3rd, cracks in the ground in those communities were spewing lava, and by Friday morning, 3 additional fissures had opened in the subdivision. Then on Friday, there was a magnitude 5.4 earthquake, followed an hour later by a magnitude 6.9 quake. That was the strongest quake to hit Hawaii since 1975. Over the next 24 hours, more than 500 earthquakes followed, 13 of them with magnitudes of 4 or greater. All of this has prompted evacuations where the lava is flowing, and it has now destroyed at least 24 homes. Scientists are there on the front lines, hoping to use their instruments to gather some data as this happens, while still trying to stay safe, of course. 2 years ago, I took a helicopter ride and landed where all of this is happening right now to try to understand about this volcano and how they study it. I was with University of Hawaii Honolulu geologist Mike Garcia, and I checked in with him via Skype just yesterday. Mike, thanks very much for joining us. First of all, just bring us up to date. What do we know about the current eruption at Kilauea?
Well, the eruption is continuing at these distal vents well away from the summit of the volcano. It's both exciting and frightening because many people are concerned whether they'll be able to move back into their houses after the evacuation of almost 17,000 people.
How does this compare to, I think there was an event in the 90s where there were several evacuations. Is this on a similar scale?
No, it's much larger. There are many more families involved in this particular situation because it's in a residential neighborhood.
So it's closer to a neighborhood, more people involved.
Right in the middle of a neighborhood. So the roadways between the houses are being cut off by the eruptive fissures.
Okay, got you. That's pretty scary. When I was with you a couple of years ago, we were talking about the long-running, slow-moving eruption there, 30-plus years, and you were thinking at that time it was winding down. What have the recent events done to change your mind on that at all?
Well, it looks like the supply of magma, new magma, has increased. So before this current activity down in the residential neighborhood, the lava lake at the summit of the volcano filled up and overflowed. So that was pretty exciting. Everybody was very curious about that. And same way at the Pu'u event, which is 19 kilometers away, the crater filled up and was overflowing. So, wow, that was great. But during that period, the volcano started to drop the levels of the lava, and it moved underground within the volcano down to this residential neighborhood about 15 kilometers away.
So what do we know about the mechanisms that would have made all that happen?
Well, to be honest, I think it took everybody by surprise because you already have 2 safety valves that are allowing the magma to come to the surface. The fact that just recently it's decided to create a new dike that propagated down the rift zone to a new location was unexpected.
So you've been studying it now for how many years? And it's still surprising you?
Oh, well, each eruption is a unique event. And during an eruption, new things can happen. So it's educational. We learn new things all the time.
Well, help me with the semantics here, because when I was with you, it was erupting. It has been erupting for 30-plus years. And then you say, we have a new eruption. There are eruptions, and then there are eruptions. Is that it?
Yes, back in 1983, we got a new eruption out on the East Rift Zone of Kilauea. And then in 2008, we got an additional new eruption at the summit of the volcano. That was unprecedented. It hadn't happened like that for quite some time. So 10 years later, we've got a third eruption going on. There's never been a recorded event like this.
Okay, so when we say Kilauea has been erupting for 30 plus years, there are eruptions within those eruptions. That's what we're talking about?
That's correct. So the early eruption started in January of 83, excuse me, and it was episodic and then went to continuous, and then we had a new event at the summit, and then this third event. So yes.
How unusual is it for a volcano to erupt for such a long period of time and then produce? It's not.
Oh, it's not. We just tend not to be aware. For instance, in Costa Rica, there's a volcano named Arenal, and it started erupting in 1968, and it's still erupting today. Likewise, there's a volcano in Chile named Realtime, and it's been erupting for many years. And then down in Antarctica, there's a volcano named Eruption. It has an active lava lake. So these are just a few of the more or less continuous eruptions that are occurring on the Earth at this time.
I've been to a few of those that you just mentioned, including Arenal, and they look a little more like a traditional volcano. In Kilauea, it's different, and the lava there is a little less viscous. Is that my recollection?
The lava at Kilauea you're right, is less viscous, so it's able to flow out much easier.
So, and that's why it's kind of a flatter, the topography is flatter. Is that correct?
That is correct. Although on the flanks of the volcano, there are some big fault scarps. So in some places where the volcano is slumping into the ocean, there are some steep areas. But overall, it's a very gentle volcano.
As I recall, you were telling me there's quite a bit of instrumentation that is at Kilauea. With all due respect to the families who are in peril here, is this an opportunity for scientists?
Oh, absolutely. Every eruption provides new opportunities. So, yes, there's a big team with the Hawaiian Volcano Observatory out in the field trying to collect data. They're looking at many different aspects, the intrusion of a dike, the gas release, what's going on there, the development of eruptive fissures, what is the pattern for that. So, yes, much is being learned.
And there's quite a bit of instrumentation already there. Is that right?
Yes, but they've set up new instrumentation. So because the eruption had been 20 kilometers to the west, there was more limited amount of instrumentation in the area that's currently erupting. So they've moved new instrumentation into this area to be able to monitor earthquakes and ground deformation.
So how hazardous is the work there right now? Do scientists take great risks getting involved to... No?
There's never a reason to put yourself at risk. So each scientist will carry a hard hat, he'll have a gas mask, he'll have protective eyewear, clothing, good boots. So yes, they will not put themselves at risk in order to collect data. They will maintain a proper distance.
Now, how about you? Will you be heading there?
I'm still finishing up teaching, unfortunately, so we've got another week or so to go. But if this eruption continues, then yes, indeed, I'll be over there.
What is the likelihood of that? I know this is a difficult thing to predict.
I think we're learning new things during this eruption. It could stop tonight, or it continue for many weeks. There have been eruptions in this area back in 1955 and 1960 that went on for many weeks. So we certainly hope that's not going to occur, but we can't rule it out. So the civil defense authorities on the island of Hawaii are warning people to be aware of the past history and to be mindful that these things could continue for more than a few days, maybe a few weeks.
For the people who live there, that's kind of an ominous thought, isn't it? But that's how these things go, and there really is no way to know, or do you think that this scientific campaign will offer some insights to people as you try to gather this data?
Well, we certainly can be hopeful as we collect new data that we'll have a better understanding. One thing that I try to do is to look at the composition of the lavas to tell us whether this is old magma that's stored in the rift zone or it's new magma coming in from the summit of the volcano. If we see new magma coming in from the summit of the volcano, it suggests the eruption might continue for quite some time. But if it's old magma that's been stored, degassed, it could shut down in a shorter period of time.
And why don't you help us understand how you can detect the difference between old and new magma?
So the old magma will have cooled, and while it cools, it loses or crystallizes various minerals, and in particular a mineral called olivine, which is very rich in magnesium. And so as that mineral forms, the composition of the lava changes, and so we can analyze the composition of lava and say, aha, this is old magma or it's new magma. And I did this back in 1983 and told the U.S. Geological Survey that, boy, this eruption could continue for a while. But we had no idea that it would continue for now over 35 years.
So it's pretty important you get out there if this eruption continues.
As long as somebody's collecting rocks and those rocks are being looked at, then we're good.
So somebody will be out there testing for the olivine. Will that occur in your laboratory, or can that occur anywhere?
It can occur in many different places. The U.S. Geologist has a team involved in doing that at the University of Hawaii at Hilo. So they're doing some preliminary work. I certainly will get samples and do more detailed work in the days to weeks that come.
And just to give us a sense of scale, how many scientists are deployed out there now, as it were?
There's a large team of tens of scientists who are working in relays where there's somebody out there 24 hours a day.
You were telling me when I met you a couple of years ago about what it's like to be in the midst of an eruption like this, doing your work. Help people understand what it's like to be out there in the middle of the night, tracking these things.
Well, it's both exciting and frightening. It's frightening in the nighttime, at least, because you don't know what is beyond your view. So something could happen that you were not expecting. So that is the challenging situation. But it's also breathtaking to be out there, to see the glow of the lava, to hear the roar of the vents, smell the sulfur. It's a total sensory experience.
Sort of gets in your blood, I guess, if you're a volcanologist, huh?
There are people that are volcano junkies, yeah.
Would you put yourself in that category?
No, I go out there when I'm needed. I don't get in the way or try to impose on the U.S. Geological Survey. But if the opportunity avails itself, I will definitely be out there.
So we had a chance when we met you to see your extensive library or catalog, if you will, of newly minted rock from Kilauea and other volcanoes in the Hawaiian chain. Have you been adding to it since I saw you yet?
Frequently, twice a month at the minimum, to monitor the change in composition over time. And I must admit, when we were looking at these recently, the compositions are going towards lower magnesium, which would suggest to us, wow, this eruption could be waning. But it roared back to life. So
yeah, we were talking about whether you're seeing the signs of things winding down, and you thought maybe you did, just as you mentioned there. So what do you think now? Does this make you kind of rethink what you've been seeing, or are you going to focus on some new data? What's the plan?
Well, certainly we're going to rush out and collect some new data, but it teaches us that you have to be a little more circumspect in terms of interpreting things, that the volcano can and will change its activity. So you can't become complacent.
Yeah, it's Mother Nature kind of throws quite a few curveballs at us. Do you think, is there some other marker or indication that maybe you've overlooked to this point? Are you going to be thinking about it that way? Or is it just better understanding the creation of this olivine that will give you the answer?
Well, certainly we should keep asking ourselves questions. That's how we learn, is we ask questions, and that forces us to look into new ways of looking at the samples, looking at other parameters to see what's going on. So, but right at this point, I would say I'm not sure what new things we're going to look for.
So what's your best guess of what happens from here?
Well, what I'd like to say is going to happen is these vents are going to shut down and the volcano is going to go back to what it was doing before. That's what I'd like to see happen.
But there's no way to know, I guess.
No, that's absolutely the bottom line. There's no way to know at this point.
I did a longer interview with Mike 2 years ago in his office. It's good background. It'll help you understand what's happening at Kilauea now. So let's talk about Hawaii in general and Kilauea in particular. This is
a well-studied volcano? True?
This is probably the best studied volcano in the world.
Tell me about that.
The early geologists came to Hawaii in 1840, and they were the first to document what was going on here. And they were struck by comparisons with the Italian volcanoes, which were well known to the Western world. And they came away thinking, wow, if we're going to study volcanoes, Hawaii is the best place because the frequency of eruptions, the easy access, you don't have many of the issues. Also, the people here are so friendly. So all these contributed to Hawaii becoming the focus of volcanological research in the world.
Access, all those things come into play. So part of what makes something well researched is the ability to get to it, obviously.
Absolutely.
Yeah.
And the fact that it's normally nonviolent. So you can get right up to the eruption site.
Tell me a little bit about that. How you characterize this eruption? It's kind of a slow burn. Would that be an accurate way to put it? Or?
Well, perhaps. It goes through fits and starts. There are periods when it is very active. It had fountains that were 400 meters high at one time back in the 80s. So it was spectacular. I used to have night duty out there, and I would monitor the volcano while the U.S. geoscientists were back sleeping. And it was a spectacular show. The roar of the volcano, the ground shaking, the heat, intensity. It was an amazing show.
What's that like, sitting there at night and being a part of that and experiencing that, feeling it?
There is no comparison. Absolutely no comparison. It's one of the most exciting things one could be experiencing.
As a scientist, I can imagine.
Well, I've done other things like dive in a submersible down 5,000 meters. That's pretty exciting, seeing terrains never been seen before. Helicoptering into some areas in Antarctica. There are lots of amazing places that a geologist gets to visit.
Well instrumented. Tell us what are the array of instruments that are part of the package right now, and how much do we know? How much do we not know?
So Kilauea volcano has a vast array of seismic instruments. There's over 50 stations that are set around the volcano to look at its activities. They're mostly concentrated in the summit of the volcano, but the rest of them are displayed around its rift zones and far distant to allow them to detect where the earthquakes are occurring and their size. In addition, they have various deformation tools that they employ, lots of GPS stations. They're using satellites to monitor the eruption. Thermal cameras now are very important to image where the hottest part of the lava flows are. And then webcams. There are webcams now in many places on the volcano to give us real-time information on what's going on.
See, you've been doing this for a few years. The amount of technology you can bring to bear is significantly improved in a couple of generations. Tell us a little bit about that.
Well, there are various kinds of instrumentation. The one we take in the field as well as the ones that we use back in the laboratory. So in the field, we now have high-speed cameras, for instance, that can document what's happening during one of these explosions that occurs at the summit with the active lava lake. So you can get thousands of frames per second of what's going on during one of these bursts. So that's spectacular. The thermal cameras to document what's going on in an area you can't approach, but you can see in vivid detail with these new thermal image cameras.
What are the big questions that you're trying to answer?
Well, with most volcanoes, you want to know when it's going to erupt. And so that's a primary concern. But in this case, where we have an eruption that's been going on for over 30 years, the big question is, when's it going to stop? So we're continuing to look at what are potential clues to indicate when this eruption might stop, because this is the longest lived eruption in the 500 years of Kilauea activity.
Really? So, and how do we know that? Because you've been around a long time, but not 500 years. How do you know that?
Right. So we use various tools like carbon-14 dating to indicate when eruptions occurred. So as well as detailed field work, you can work out when there were eruptions and approximately for how long.
What have you been able to piece together? Do you have any sense? Do you have any? Are there signs in there? There are signs in the lava that give you some clues as to what's going on and when it might stop.
One of the tools we have is looking at the chemistry of the lavas, and particularly we use that to infer the temperature of the magma. So what we've seen is a long-term decrease. Initially, the lava temperature was low. It increased, the eruption roared upward, and now it's been slowly waning and we see the temperature of the lavas indicating a decrease. So we think this eruption might end in the near future, but it's ended several times in the past. It was quiet in 1997 for a month. and then it restarted.
In 97, did you think it was over?
Yes, everybody thought it was over. It went quiet. And then a helicopter pilot flew over this cold pit and noticed, oh, there's something glowing down there. And sure enough, within a few days, it was erupting again out of that pit.
So we're kind of still in the dark on this, aren't we?
We have much to learn, and that's the exciting part. As we gain more information, we can ask better questions and bring in tools that help us resolve those questions.
Is there a chemical signature potentially? And I guess we won't know that until it's way in hindsight, I suppose,
Well,
right?
we can use the chemistry to help predict, like are there changes in the gases? Are there changes in various parameters that would indicate something's going on at depth that might lead to the end of the eruption. We saw this back in 1924 when there was a collapse of the Summit lava lake, and that shut down the volcano for several decades.
Oh, it did. And so was there something looking back on the chemical composition at that time that was telltale, maybe?
Yes.
What was it?
Well, we looked at various things like isotopes, strontium and lead. They peaked at the time of the collapse. So they were increasing, and then they dramatically decreased at the time of the collapse.
Are you seeing any evidence of a similar pattern now?
It's going the opposite way. It's going the opposite way. So it's not clear where this is going to lead. And that's the exciting part. We don't know.
It's a real riddle. Give me the mechanisms we're going to see. We're going to see on Sunday, of course. How do you go about your work?
Well, there are many aspects. The first aspect is getting in the field and sampling the rocks. So that's the primary start. So this is an example of rock that was collected last week, and we'll go out and collect a fresh sample. So we want a sample that's collected molten, so we know the time of its birth. And in some cases, we're collecting samples every hour, sometimes every day. And in cases where it's not changing very much, we go out monthly. But the idea, this is where it starts, to have a piece of fresh rock where we know when it was born. And from that, we bring it back and do a series of chemical analyses. We do probably 45 different separate elemental analyses to characterize what's going on in these rocks. We also look at isotopes to get a better understanding of what's going on in the system. Each of the processes within the volcano leaves a fingerprint. So over the years, we've been able to develop an understanding of what those fingerprints are and what they tell us about what's going on in the volcano.
It's fascinating. It's detective work is what it is.
Absolutely.
Right?
That's absolutely the way I approach it anyway.
You're a geologic gumshoe. So when I got to ask you, you said in the near future you think it might stop. When a geologist says near future, I don't know what that means. That could mean an epoch, right? I mean, what do you mean by in geological scales or in our scales?
In our scales. I would think in the next few years it's likely to stop.
I remember a few years ago, there are probably people you know, there were some geologists, volcanologists who were actually brought up in charges in Italy for not predicting properly a volcano.
That was an earthquake.
Oh, it was an earthquake? Okay.
Yeah.
But the point is, are we ever going to get to a point where scientists can reliably predict these things?
I hope so. I hope that's in our future, that we'll be able, particularly in areas where you have a great potential loss of life, like in Italy, Vesuvius. If that were to erupt again, millions of people might die. So having the knowledge of that volcano, as well as volcanoes in general, will hopefully allow the volcanologists in Italy predict that eruption, as well as eruptions elsewhere. So that's our goal. It's just like with earthquakes, to better understand, so at least we have some warning, maybe not more than a few minutes, but at least some warning of what's going to happen.
Prior to the eruption of St. Helens, there were warnings, right? There wasn't. There was that guy. Who was the guy who stayed in the?
Yeah, Harry. His first name was
No.
Harry.
Was it Harry?
Truman.
Harry Truman. That's the other Harry Truman. That's right. And he stuck it out. But I do recall that there had been an evacuation prior, so they must have some indications, right?
Certainly, there was a good indication that the volcano was active. What they didn't understand at the time, and we only learned through hindsight, is that the bulging that was going on the north side of the volcano was telling us that magma was coming in, and that would lead to a sector collapse, as it's called. The whole north side of the volcano gave way and formed that giant landslide that killed so many people.
Now that, of course, that was a pyroclastic flow. It's a different kind of volcano than what we're going to see.
Well, to
right?
be honest with you, we're gaining a new understanding of Kilauea. And in the last few years, we've realized that Kilauea has been more active explosively. It's erupted explosively 60% of the time, whereas lava flows have only occurred 40% of the time.
Interesting. So it's just our personal reference. We assume it's...
That's right. Over the last 200 years, the activity's been dominated by lava flows. But prior to that, there was a 300-year period in which my student is focusing on that was characterized by explosive activity.
Interesting. So now, in the case of the lava flow that you're experiencing these days, it's almost like a slow-motion train wreck. You see it coming, and unfortunately, it starts to encroach on people's homes and so forth. Tell us a little bit about the potential jeopardy that people face.
Well, certainly there has been several episodes where the lava was able to define a well-formed channel, and then it was carried long distances from the vent. So about 125 homes have been destroyed back in the 90s. When the eruption became more vigorous, it formed tubes, and it brought the lava down to the coastline. And then just recently, in 2014, 2015, there was a particularly strange event where lava found a crack and traveled along this crack and then came out and headed towards the outskirts of a town called Paoa. And there was a lot of concern because tens of thousands of people were going to be cut off by the lava flow, so they couldn't get to and from work, to and from school, to the market, any other way. But fortunately, for whatever reason, the lava flow stopped just at the edge of the community. So we were very lucky.
This is a reminder of why it's important to learn this kind of stuff.
The same community was covered 300 years ago by lava repeatedly. So it's not as though this was a fluke event. This has happened repeatedly in the volcano's history.
Are you sort of humbled by what you don't know after all these years?
Absolutely. That's one thing age teaches you, is to be mindful of what you don't know rather than to emphasize what you do know.
At what peril do you put yourself studying all this?
Less so than being in a car. I think I understand the circumstances well enough, so I prepare in advance for what I might encounter. We bring gas masks, we bring various tools. We look at the environment before we land, before we get into trouble. Things might change, and we try to plan for that change, but I feel confident that we're not at risk.
There are old geologists and bold geologists, but no old, bold geologists. Is that it?
No, that's certainly not true. There are a few geologists that have been killed during eruptions, and it was mainly just bad luck, where they didn't anticipate an unpredictable event. Mount St. Helens, there was some geologists caught during that eruption. The eruption in Japan, the 1991, that killed a bunch of geologists as well.
Yeah.
They thought they were safe, but unfortunately something unpredictable occurred and they were killed.
You first started looking at this in 79, you said? Is that right?
1983.
83. So from 83 to now, as you look back and look at the trends and the data and everything, what is the overarching trend that you've seen there at this particular volcano?
Studies of other volcanoes have focused on taking a sample here or there to document an eruption. So much of what we know about many eruptions around the world are based on one or two samples, like my own volcano in the Philippines. I've been very excited to learn more about that volcano, which also erupts frequently. But unfortunately, people don't collect samples in the same intensity that we have done it here at Kilauea. And what we've learned at Kilauea by perhaps the most detailed sampling that's ever been done on any volcano in the world is it changes. And those changes are reflected in the compositions of the rocks. So it's teaching us things that we never knew existed because we just hadn't sampled in enough detail. So for instance, what's happening underground and where is magma stored? How long is it stored? And how does it find its way from the deep mantle to the surface, and what goes on in between. So these are all kinds of exciting things we're now able to look at with a long-lived eruption, but we could never have approached with one of these typical short-lived eruptions we've had in the past.
So if you were to compare that rock, that hot off-the-presses rock, to what you found in 83, would they be extremely divergent?
They would be very divergent, yes.
Like, can you give me a couple examples how it would differ?
For instance, lead isotopes is one of the things we look at. Calcium-aluminum ratio. The major elements, trace elements, isotopes are all different, and they change in cyclic patterns. It's exciting in terms of understanding what's going on at depth.
It's interesting because we've just been doing a story on El Nino, weather forecasting. And, one of the questions we keep asking is it ultimately predictable or is it just chaos? And I suppose a similar question could be posed to you. Is it possible that this may not be predictable?
It's certainly possible, but I think we have to endeavor to see if there's order in this apparent disorder. So that's our challenge, to see if we can find a pattern in each of these different volcanoes that can help us understand volcanoes in general.
It might be there in that rock. You just don't know yet.
We'll find out soon. One of the things I've been looking at is oxygen isotopes to try and document what's going on before the eruption occurs. And what we found that there's substantial contamination of the magma before it erupts. In the magma chamber, it's melting the surrounding country rock. And that rock is contaminating what we see at the surface. And we never appreciate the extent at which that goes on until this new study.
So magma makes more magma in that chamber.
By melting the surrounding rock, right. We knew that went on to some degree, but not the scale that we're seeing at.
And how does that help you one way or another predict or understand? Or?
Well, it's part of the process of understanding how the volcano does what it does, of being able to look at each of these things. So we'll decide to focus on a particular aspect of the volcano, and we'll pursue that vigorously to try and understand, hey, what's going on in this particular case? Because one of the fundamental concerns has been, where does the magma that feeds this volcano come from? And one idea is it's coming from Japan or somewhere in the distant past where the plate subducted and went all the way down to the core and came back up. And so we're looking for fingerprints of that process. And one of those fingerprints is potentially oxygen isotopes. And people had seen a disturbing trend in the oxygen isotopes. Said, well, gee, these things have been contaminated. Well, what we've been able to show is that contamination is in the crust. It's not deep in the earth. Wow. And so we've come away with a much different perspective than before we started.
But there's reason to believe this magma is flowing those kinds of distances.
Oh,
potentially.
Yes. We have pretty confident impressions that, yes, it starts with a recycling effect of going into the subduction zone and going deep into the mantle, all the way perhaps to the core mantle boundary, and then getting recycled in hot plumes that feed volcanoes like Hawaii.
Yeah, I mean, I just imagining something I probably saw in high, grade school on volcanoes, and you imagine this pool down toward the center of the earth, and it goes straight up. That's not really the way it goes.
Well, it's similar in the sense that it's going down perhaps very slowly, and it ponds in deep mantle. And it's convection cycles, we think, in the deep mantle that cause the earth to rise up, and you get these plumes that ascend in places like Hawaii, the Galapagos, and feed volcanoes.
A few days after that interview, we flew with Mike to Kilauea. We watched as he scooped up the lava, newly minted earth, and then quenched it in water to be cooled and eventually returned to his lab for study. In between the sampling, which was fascinating on its own right, we talked right on that seemingly alien landscape.
All right, so just tell us where we are, Mike.
We're here on the east rift zone of Kilauea volcano, out where the active flows are oozing out onto the surface. They originally came up in the vent that's behind us about 1 kilometer, and have moved down the rift zone through a sub-area underground lava tube, and then now are oozing out in the surface.
So is there kind of what's the strategy to do your work when you're out here?
We look for an area where we can be upwind of the active flows. And so we're looking for a safe area where we can approach the lava. The wind is at our back, blowing the heat and the volcanic fume away from us. So we can then approach it, grab some molten material, and move away.
So always upwind, approach gingerly, watch where you're walking. There's a lot of things to be wary of, obviously. This is potentially hazardous.
Potentially, but I've been doing this for over 30 years, so I have a good feeling for what's safe.
What does it tell you by going over to that oozing hunk of brand new earth?
Yes.
And putting your hammer in and throwing it in that can and quenching it? What can that ultimately tell you when you take it back to the lab?
We'll get a lot of information out of that. For instance, what temperature is the lava? By analyzing the chemistry, we can say, right, this was around 1130, 1140 degrees centigrade. And then from that, we can also look at the minerals that are present and talk about how long they've been stored in the volcano, as well as how it was formed at depth, down in the mantle. So we get a lot of different kinds of information from that one sample.
What's going on beneath our feet here?
The earth is growing. The earth is growing. We're adding new material to the Big Island. It's getting ever bigger.
The big island it's the bigger island, even as we speak, huh?
It's bigger and bigger.
So it's kind of a work in progress. Can you describe in detail though what the channel for the lava is, or is that the fundamental aspect of your research?
Well, certainly at the surface, what they use is thermal cameras to map out the migration of lava underground. So these cameras can diagnose where the hot material is. But once you get out in an area like this, it's everywhere. It's underneath the surface.
So there are multiple volcanoes, a few active, some dormant. Are there extinct volcanoes on the Big Island or just dormant?
Yes, on the north end of the island, Kohala volcano is extinct. It last erupted about 100,000 years ago. So we think that one's extinct.
So are they all kind of interconnected, we think?
No.
Okay.
I think they're not connected. What erupts at each volcano is distinctly different. The chemistry tells us that they're coming from many different parts of the mantle plume.
Interesting. So those olivines that we saw under that microscope, are we standing on them now too?
Yes, your feet are on top of olivines, that's right.
And that's a very useful signature for you, right?
Absolutely. That's the key mineral that we see in these rocks. It is the first mineral to form, and in many cases the only mineral to form in these rocks, which makes it a beautiful, simple sample to work on.
Because it gives you what specific information? I know this is slightly repetitive, but go ahead and say.
Well, we get all kinds of information. We get what the temperatures, we get time scales. It's a very effective mineral for looking at magmatic processes within the volcano.
How close then, how many more trips like this do you think you have to do before we can come up with a way of kind of predicting these things?
I can't see that we'll know when these eruptions will occur. We hopefully can tell when they're going to stop. But when next eruption is going to occur, that won't happen from sampling lava.
This eruption has been going now since the mid-'80s, right?
1983,
and
January.
Pretty much, there was a brief stop.
It has stopped several times for as much as a month, but it started right back up again. So the mantle is producing an enormous amount of hot material that's coming out of Kilauea. This is probably one of the most active periods of the historical record of Kilauea.
Mike Garcia, thank you very much. We appreciate the risks you take on behalf of learning more about volcanoes. Right now, Mike is tied down teaching in Honolulu, but if the eruption continues and he gets freed up, you can bet he'll be there trying to get some more samples to help understand how these eruptions happen and how one day they might be better predicted. That's Miles to Go. I'm Miles O'Brien. Thanks for listening.